At its zenith, Rome was a bustling metropolis of over 1 million people. But how did this ancient superpower quench its colossal thirst? Water was the lifeblood of the empire, crucial for the iconic baths, ornate fountains, and the daily survival of its people. The demand for fresh, clean water was immense, far exceeding what the Tiber River could safely provide for a growing population. The Roman solution was an engineering marvel that would define their legacy: the aqueduct, a man-made river carried on stone. These weren't just simple channels. They were sophisticated systems, meticulously planned and constructed to last for millennia. Some aqueducts stretched for over 50 miles, bringing millions of gallons of water to the city every single day. This constant, reliable flow of water is what allowed Roman cities to grow to an unprecedented size and complexity. But how did they achieve this incredible feat without modern technology, pumps, or electricity? The secret is deceptively simple. It all came down to a mastery of one fundamental force of nature that governed every aspect of the aqueduct's design. Join us as we uncover the genius of Roman engineering and reveal how their legendary aqueducts actually worked. The journey of the water began far from the city, high in the hills or mountains, at a pristine and reliable source. Roman engineers, known as aqueducts, would scout the countryside, searching for the perfect spring or stream to tap into. They meticulously tested the water's purity, taste, and flow rate, ensuring it was fit for the citizens of Rome. Once a suitable source was confirmed, they constructed an intake structure, or captatio, to collect the water. These were often small dams or spring houses designed to capture the flow and filter out initial debris like leaves and silt. From this collection point, the water would enter the main channel, or specus, to begin its long, gravity-powered journey. Surveying the route was the next critical step, requiring immense precision to plot a course back to the city. The path had to navigate hills, valleys, and plains, all while maintaining a very specific, continuous downward slope. This initial phase of finding the source and plotting the course could take years of careful planning and calculation. Choosing the right source and path was the foundation upon which the entire success of the aqueduct depended. The true genius of the aqueduct lies in its elegant simplicity. It wasn't powered by pumps, but by gravity alone. Engineers designed the entire system with a continuous, gentle downward slope from the source all the way to the city. The gradient was incredibly precise, often dropping only 1 foot for every 300 feet of length. If the slope was too steep, the rushing water could erode and damage the channel, causing breaches and costly repairs. If the slope was too shallow, the water would stagnate, allowing sediment to build up and block the flow completely. To achieve this perfect balance, Roman surveyors used sophisticated tools for their time, like the chorobates. This device worked like a giant spirit level, allowing them to measure the gradient with remarkable accuracy over long distances. They would painstakingly check the slope at every stage of construction, ensuring the gradient remained constant and true. This constant, gentle slope ensured a steady, manageable flow of water moving continuously towards its destination in Rome. This mastery of gravity and gradient was the invisible engine that powered the entire Roman water supply system. When we picture a Roman aqueduct, we imagine towering arches, but this is a common misconception about their construction. In reality, about 80% of the aqueduct's length was hidden from view, running underground or at ground level. Whenever possible, engineers would dig a simple trench, construct the stone channel, and then cover it with earth. This cut-and-cover method was cheaper, faster, and protected the water from contamination, evaporation, and seasonal temperature changes. When the aqueduct's path encountered a hill or a mountain, the Romans didn't always go around it. They tunneled straight through. Teams of workers would dig from both ends of the hill simultaneously, using fire and water to crack the rock. Their surveying was so precise that these two tunnels would meet almost perfectly in the middle, a remarkable feat of engineering. These underground sections were the unsung heroes of the system, quietly and efficiently carrying water across the landscape. Vertical shafts, or puttae, were dug down to the channel every 100 feet or so for inspection and maintenance access. So, while the bridges are what we remember, the vast majority of the work was a hidden subterranean marvel. So if most of the aqueduct was underground, why were the iconic, towering bridges necessary at all? When the carefully graded path met a deep valley, river, or low-lying plain, the engineers had a problem. To maintain the precise gravitational flow, they couldn't just dip the channel down. They had to carry it across. This is where the magnificent arched bridges came in, lifting the water channel high above the ground. The key to their strength and longevity was the Roman arch, a simple but incredibly effective architectural innovation. The arch redirects the massive weight of the structure downwards and outwards into the support pillars, creating immense stability. Many were built using opus cementitium, a form of Roman concrete that was incredibly strong and durable. They would construct wooden scaffolding, build the arches stone by stone, and then place the water channel on top. Some aqueduct bridges were truly colossal, featuring multiple tiers of arches to cross the deepest valleys. These bridges were not just functional, they were powerful symbols of Rome's wealth, power, and engineering dominance. Let's take a closer look inside the specus, the water channel itself, which was the heart of the aqueduct. These channels were typically about 3 feet wide and 6 feet high, large enough for a worker to walk through. To prevent leaks and water loss, the interior was coated with a special waterproof cement called opus signinum. This remarkable material was made by mixing concrete with crushed terracotta tiles, creating a durable, impermeable layer. Most channels were covered with stone slabs. This prevented sunlight from encouraging algae growth and kept the water clean. However, even with these precautions, the channels required regular maintenance to keep the water flowing smoothly. Calcium carbonate from the water, known as sinter, would gradually build up on the channel walls, restricting flow. Workers would enter the channel through the vertical shafts and chip away these mineral deposits to clear the passage. In some places, these sinter deposits were even mined and repurposed as a decorative building material. This constant cycle of inspection and cleaning was vital to ensuring the aqueduct system operated for centuries. But what happened when a valley was simply too deep or wide for even the most ambitious arched bridge? For these extreme challenges, Roman engineers employed a brilliant and daring solution, the inverted siphon. Instead of building a bridge across, they would channel the water into a series of reinforced lead pipes. These pipes would run down one side of the valley, across the bottom on a low bridge, and then up the other side. The system worked on a simple principle: water seeks its own level. The exit point was built slightly lower than the entry. As water flowed down into the siphon, it built up immense pressure, known as hydrostatic head. This pressure was powerful enough to force the water back up the other side almost to its original height. This was a huge engineering challenge. The lead pipes and their joints had to be strong enough to withstand the immense pressure. Siphons were incredibly expensive due to the cost of lead, so they were used only when absolutely necessary. The use of inverted siphons demonstrates a sophisticated understanding of physics that was far ahead of its time. After a long journey, sometimes spanning more than 50 miles, the water finally reached the outskirts of Rome. But its journey wasn't over. The water flowed into a primary distribution tank, the castellum aquae. This impressive structure acted as a terminal reservoir, slowing the water and allowing any remaining sediment to settle. Inside the castellum, a complex system of sluice gates and outlets controlled the flow into the city's network. From the main castellum, water was channeled into smaller, secondary tanks located throughout the city's different districts. A network of underground lead pipes, called fistulae, then carried the water from these tanks to its final destination. The pipes were often stamped with the name of the emperor or the manufacturer, helping to regulate the system. The diameter of the pipe determined the amount of water a user received, which was the basis for the water tax. This distribution hub was the critical transition point from the massive scale of the aqueduct to the fine-grained city grid. It was a highly organized system, ensuring that Rome's lifeblood was managed and distributed efficiently across the vast city. Once distributed, where did all this water go? The Romans had a clear hierarchy for its use. The highest priority and largest share went to the city's magnificent public baths, or thermae. These were not just places to get clean. They were social hubs with libraries, gyms, and gardens, all powered by water. The next priority was the hundreds of public fountains, or lacus, scattered throughout the city's neighborhoods. These fountains provided free, continuous flow drinking water for the general population, accessible to everyone, rich or poor. Water was also used for public necessities like flushing the latrines and cleaning the streets and sewers. Only after these public needs were met was water allocated for private use, and it came at a price. The emperor and the very wealthy could pay a water tax to have a direct pipe connected to their private villas. This was a significant status symbol, providing the ultimate luxury of running water for private baths and ornamental fountains. This system ensured that while the rich enjoyed luxury, the essential needs of the entire populace were always met first. Amazingly, many of these aqueducts have withstood the test of time, with sections still standing nearly 2 millennia later. They are a powerful and enduring testament to the skill, ambition, and incredible ingenuity of Roman engineers. These structures were more than just water conduits. They were the circulatory system of the Roman Empire. They enabled the growth of large, dense cities, supported public health, and facilitated a way of life previously unimaginable. When the aqueducts fell into disrepair after the fall of Rome, the population of the city plummeted dramatically. This highlights just how critical this continuous supply of fresh water was to sustaining a large urban population. The core principles of gravity-fed water systems, perfected by the Romans, are still fundamental to modern civil engineering. From the materials they used to their methods of surveying, their influence on how we manage water is undeniable. They were a monumental public work that served the people, demonstrating a commitment to civic infrastructure on a grand scale. The Roman aqueduct remains one of history's greatest engineering achievements, a river in the sky, born from pure genius.